Okay, this is part 2 of RLC circuits. For whatever reason, the video gave out initially. So I believe where we stopped was we had just finished talking about the overdamped case. We then said that the third possibility is where your R over 2L squared is less than 1 over LC, meaning you get a negative term under the square root sign for the poles, which means your poles are complex conjugate pairs given by minus sigma plus j omega and minus sigma minus j omega. That yields to a solution, a general solution that looks like a damped sinusoid. How much is sine and how much is cosine and what A and B are depends on initial conditions and things like that. But nevertheless, you have complex conjugate pair roots, and so what that means is that you generate a response that looks sinusoidal but is damped. Sorry, that's supposed to be curvy, but dies away. This is what you modeled on your multisim model that we refer to as underdamped, primarily because it oscillates a lot. Damping occurs due to resistance in the circuit. If you had no resistance in the circuit, then R would be 0, and your solution would be purely sinusoidal. You'd have LC ringing. Because you add the resistance, you begin damping. And so depending on the relative values between resistor, inductor, and capacitor, you can be underdamped, you can be overdamped, or you can be critically damped. The pulse power people often design a critically damped circuit because it tends to give you the most energy in a single pulse over a shorter period of time than, say, your overdamped. The fastest one, as far as how quickly this oscillation occurs, is the underdamped. It's going to have a shorter rise time, but unfortunately it's going to have a reversal. And so in a lot of applications, you don't necessarily want a very big voltage reversal. You don't want ringing, so you don't always want the underdamped circuit. Hence, you try not to design this for most practical applications.